as far as I can remember, we were talking about momentum and its conservation, right? Why was momentum conserved? Because of Newton's third law. Action was equal to reaction. So in any system, if I have a closed system, the forces between the components of the system always form an equal and opposite pair, right? Which means the total momentum of the system is conserved if it's a closed system. So now in this question, do I have a closed system? Well, maybe. You know, whoever has asked this question did not specify whether there was friction on the table. But let's be gentle to our professor. Let's say that he really specified there is no friction. So if there is no friction there, yes?
You have also not given the word velocity to second velocity.
It's 0, as shown. So, okay. Now, so let's say that there is no friction and second velocity is 0. But in this case, whatever forces, gravity force acts, weight of these objects act on it, but they are cancelled by the normal forces. So the sum of the external force on these two objects is 0, which means this is a closed system. For any closed system, momentum is conserved. So initially, before the collision, I have this 3m moving with v and this m not moving. So what's the initial total momentum? 3mv to the right. After the collision, how do these objects move? They all are stuck to each other, so they move with a common velocity. So let's call this is 3m, and this is m. They got shorter when they hit each other. That's a joke. You're supposed to laugh, right? So let's call this V final. P final is going to be 3m plus m, 4m times V final. Initial velocity is, initial momentum is equal to final momentum. 3mv is equal to 4mv final. M's cancel, so V final is 3 over 4 V. How many of you found this result? Excellent. Great. So not much was lost over the last week. You still retain your memory. That's great. Now let's solve the second part. What's the initial energy of the system? Well, initially I have 3m moving with velocity v plus m moving with velocity 0. So this is 0. So initial kinetic energy is 3/2 mv square. How about final kinetic energy? Final kinetic energy is, now these objects collapse into a single mass of mass 4m, and V final square, so this is going to be 1 over 2, 2m. V final is 3/4 V squared. So if I figure out, this is 2m 9 over 16 V square. So this is 8. So this is 9/8 V square. What's the change in energy? So E final minus E initial. E final is 9/8 mv square. E initial is 3/2 mv square. So this is going to be 9 over 8 minus 12 over 8 times mv square. So it's going to be minus 3 over 8 mv square. I'm very happy that I found a negative result. Final energy is less than the initial energy. How did the energy conservation work out in this case? well, you may say energy is not conserved, but that's just the mechanical energy which is not conserved. Presumably during this collision, there are some new chemical bonds forged between these objects, or whatever else. Maybe something get crushed there, maybe some heat was released, maybe these objects also released some sound when they crashed into each other, right? So mechanical energy was converted into all those kinds of energy. So the energy lost, you can say 3/8 mv square of energy was dissipated during the collision. All right. Any questions? No. Now, for historical reasons, such a collision where the objects actually completely stick to each other and move with the same velocity after the collision is called a total inelastic collision. Which means objects stick to each other. Now, let's investigate the other limit. Again, I'm defining a new term, an elastic collision means no energy is lost during the collision. And anything in between, right? So if some energy is lost, but the objects really do not stick to each other, they haven't formed the bonds, enough bonds to keep them together, that's called an inelastic collision. Okay? So basically whole range between these two extremes is called inelastic collision. This is just some terminology. This is just some naming things. But let's actually investigate this elastic collision business in more detail. It's going to be very important because when macroscopic objects like these two masses actually collide, there are a lot of places where you can actually channel your energy into. You can turn it into heat, you can turn it into sound, you can turn it into new chemical bonds. So most collisions of most macroscopic objects are inelastic. But when I go to the microscopic, if I scatter one electron from another electron, in most cases, there is no place I can actually easily dump my energy. That's why most collisions, when I go to the atomic regime, are going to be elastic collisions. So it's actually a good idea to investigate these collisions. There's a question.
In reality, does collisions in the extremities happen?
Well, I mean, yes. You know, if you have a big car crash, right? Two objects really move as one after that. Okay. So total inelastic collisions do happen. Okay. How about elastic collisions for big objects, for macroscopic objects? That's almost always not possible to get a totally elastic collision. The best objects that collide, macroscopic objects which collide almost elastically, are very squishy objects, right? Like, you know, balls. Some balls may have what's called an elastic coefficient of 0.99, so they can be very, very close to elastic. But do not think of collision just as a collision between the atoms of a particle. Let me tell you another example of collision. When I actually send a satellite to Mars, okay, and it's deflected by its gravity field and it goes to another way, that's another collision. There is some exchange of momentum and energy between the planet and the satellite. That's a collision, and that's a very elastic collision. There is no energy lost during that. Okay, so elastic collisions for microscopic objects as well as inelastic are important. We should study that. Okay, good question though. Any other questions? Yes?
I know always momentum has should conserve, but I couldn't understand why energy is conserved.
Energy, okay, so, okay, it's not like momentum conservation. Mechanical energy conservation is an assumption we make. If there are no places that we can actually give energy to, okay? For macroscopic objects, there is always heat. You can always give some energy to heat, okay? But when I'm talking about, let's say, the collisions of molecules, there are not enough degrees of freedom I can actually dump this energy into. When I scatter an electron from another electron, unless I start creating positron-electron pairs or creating other particles, it would be very hard to turn my initial kinetic energy into something else. That's why most collisions in the atomic regime, if you want, are elastic. Yes?
When an electron releases a photon.
That's an inelastic. That's a way of dumping energy into light. So that's inelastic.
Momentum is still conserved.
Momentum is always conserved. All right, good. So let's solve one example. Energy is conserved. Let's take the same system, almost the same system. Let's say that there is no friction here. And I send an object of mass, let's say 2m, with velocity v, onto an object of mass m with initial velocity 0. So there is no velocity. All right. Now, if these objects collide elastically, find the final velocities of both objects. So initially I have 2m going with v and m just staying there. And finally, let me say that m is moving with velocity v1 to the right and 2m is moving with velocity v2 to the left. Okay? Let's figure out what v1 and v2. Now I have how many unknowns? Now I have 2 unknowns. So I need 2 equations. The first equation is momentum conservation. Momentum is always conserved. Where will my second equation come from? Elastic energy conservation. So momentum is conserved. That will give me one equation. Energy is conserved. That will give me my second equation. What's the initial momentum in this state? 2mv to the right. How about the final momentum? That is right. I'm looking at momentum to the right. So mv1 is positive while 2mv2 is negative. Do not forget that momentum is actually a vectorial quantity. All right? Are we on the same page? Okay, good. So I'm going to say that momentum is conserved. 2mv is equal to mv1 minus 2v2. And now my energy is also conserved. What's my initial energy? 1/2 2m v square. How about my final energy? 1/2 m v1 square, 1/2 2m v2 square, plus or minus? Plus, right? This is a scalar quantity. You should never use minus signs with kinetic energy. But be careful. I see a lot of students making a mistake at this point. Right? That both of these quantities are positive. So if energy is conserved, 1/2 2mv square must be 1 half m v1 squared plus 1 half 2m v2 squared. So two equations, two unknowns. I should be able to handle this. I should be able to solve these equations. All right? Let's simplify both of them a little bit. M appears on the right and left hand sides all the time. 2 appears 1 over 2 coming from the kinetic energy formula. So here I would have 2v is v1 minus 2v2. Or let me write it in a other way. I'll say v2 is v1. Let's do it slowly. 2v2 is v1 minus 2v, or v2 is 1 over 2 v1 minus v. Right? I am extremely tired. I really flew for almost 30 hours before coming to Turkey. Okay, so today you should be more careful about my calculations. Check my algebra. If I do something wrong, correct me. All right? Now, 2v square is v1 square plus 2v2 square. But I know what v2 is. Let me just plug it in here. 2v square is v1 square plus 2 1 half v1 minus v squared. All right? So what do I have? 2v squared is v1 squared plus 1 half v1 squared. Then what do I have? Minus v1 to v1 v, right? No, I think I'm correct now. 2 plus 2v squared. I'm multiplying by 2, right? So this is 1/4 v1 squared. It becomes 1 half v1 squared. Here I have v1 v. I'm multiplying by 2, so it's 2 v1 v. Okay? Am I correct? Oh, good. Now, 2v squares cancelled on each side. What do I have? 0 is 3 halves v1 squared minus 2 v1 v. v1 3 halves v1 minus 2v. So this is a quadratic equation, and it will always be a quadratic equation, right? V square. Quadratic equations have two solutions. Now this is v1 equals 0 solution. In the other hand, v1 is minus 4/3 v solution. Where? No, I actually, it's a multiplication, right? So it's, I think it's correct. v1 is plus 4/3 v. Thank you. Now, why do I find two solutions? Well, one answer is, of course, it's a quadratic equation. But how did I find these solutions? I wanted momentum to be conserved and energy to be conserved, right? What would have happened if these two objects passed through each other without colliding? Would momentum be conserved? Yes. Would energy be conserved? Yes. So my equations must also find that solution, the initial state. One solution of my quadratic equation must be the state before the collision. Is that so? Yes. It finds v1 equals to 0. This is actually before the collision. So that's not the solution I'm looking for. This is if these objects pass through each other without colliding. Okay? How about the second one? Well, that must be the solution I'm actually looking for. And so v1 is 4/3 v. What was my equation for V2, it was 1/2 V1 minus V. So it's 2/3 V1 minus V. So it's minus 1/3 V. Hey, let's find the. So this is M. It's going with 4/3 V to the right. And I showed V2 to be to the left. But what did I find? I find it to be minus 1/3 V, which means I guessed the direction of the velocity wrong when I was writing my equations. In reality, actually, it was going to the right with 1/3 V. Now, first thing first, does it make sense to you for 2m to keep moving in the same direction? Most students would say, I would expect it to go back. Because after a collision, usually we expect an object to go back. But think of a big truck. If it collides elastically with a fly on the road, would you expect it to go back? No, it has too much momentum. It will just keep on moving in the same direction. Here, the incoming mass is 2m. It's twice the mass of the object that's sitting there. So it has too much momentum to turn back. It will actually keep going in the same direction. So it does make sense. If I've actually sent a mass with less than m, that would come back. Okay? So that's good. The nice thing about these problems is that I can very quickly check my momentum and energy, my final momentum and final energy. Let's check. What's the final momentum? P final is 1/3 V times 2m plus 4/3 mv. So it's 6/3 mv. This is 2 mv. It's exactly my initial momentum. So momentum conservation we have actually handled correctly. So this is a check. How about final energy? 1/2 2m 1/3 v square plus 1/2 m 4/3 square v square. So what is that? M 1/9 v squared plus 16/2 times 9 m v squared 1/9 plus, this is 8/9, right? 8/9 v squared. So it's mv squared, and that was initially, my initial energy was 1/2 2mv squared. So it's mv squared. So energy is conserved, momentum is conserved, which means we have actually found the correct momenta, correct velocities in the final case. Okay, so I think it's a good way to check your results. It's easy to calculate these things. You can always check your results. But don't forget, whenever you're looking at an elastic collision, you'll have a quadratic equation, and this quadratic equation, one of the roots you already know. It's the state before the collision. And you're actually looking for the other solution. Okay? Good. Now, can I always find the final velocities in an elastic collision? Who says no and why?
If energy is not conserved,
But that's not an elastic collision.
you can always find.
So, okay, so the question is, do elastic condition, or does elastic condition determine final velocities completely? Who says yes? In one example, I've already done it. Who says no? Oh, come on. 2 people said yes. Okay. No one said no. There are 53 sheep in my class. That doesn't happen. I'm asking again. Who thinks that elastic condition actually finds the final velocities?
What do you mean by the final velocity?
Well, the final velocities after the collision. If I tell you that it's an elastic collision, does that completely determine? Can I always solve for them? How many of you think yes? How many of you say no? I can't believe this, really. I mean, come on, you're college students. You should have an opinion. I'm very disappointed. So, okay, two hands. That's good. Someone is actually helping his friends. Now, that's terrible because it basically tells you that you did not understand the question, right? So the question is, if I know that the collision is elastic, does that determine the final velocities completely? And sorry, if the initial velocities are known.
Actually, we can find the final velocities empirically.
Empirically?
Which means you didn't give the numbers, but
Symbols, yes, we can. Yes, you're right. I mean, I can solve for these velocities as a formula if you want. Okay, find it. Yes, that's true. So if I know the initial state, if I know the system is elastic, I can find the final velocities for an elastic collision only if my collision is only in one dimension. Why? Because I'll have two final velocities I need to find. How many equations do I have? Two. Momentum conservation and energy conservation. What happens if I have 2D? If I have, let's say, if I have actually, discs on ice, what's the name of that game where they throw? What curling? Yes. So curling. Does anyone know? Does everyone know what curling is? Okay, good. So curling is a game where they have these heavy cylinders, stones on ice, and I don't know the object of the game, but they throw it, and they knock into each other. So let's say that I have my initial velocity in this case, one stone hitting another stone, and at the end of the day, so this is before the collision, some collision happens, and then they go with the final 1 and the final 2. Now, how many equations, how many unknowns do I have? If this is 2 dimensions, I need to find the components, x and y components of the velocities for both objects. So I have 2 unknowns here and 2 unknowns here. All right? Which means I have 4 unknowns. But how many conservation laws do I have? Well, I have momentum is conserved and energy is conserved. But momentum is conserved as a vector, which means it will give me 2 equations. But energy conservation is, it's a scalar, it's just a number. So it gives me only 1 equation. What does that mean? It means I cannot solve for the final velocities just in terms of energy conservation and momentum conservation. And does it make sense? Yes, of course it does make sense, because in 2D, let's say I have 2 cylinders that collide head-on. Okay. In this case, I pretty much expect them to go back or forward on that line. That line would not be broken. But if these objects are hitting not right on center, there will be the amount where the centers are displaced from it. Okay. Basically, how much you're off the target, that is going to give me a different collision. That's going to give me a collision where these 2 objects are going to be scattered in different directions, right? So basically, the results of my collision depend on the collision, the details of the collision itself in 2D. It will actually be even harder in 3D, because in 3D, I'll have to find 6 unknowns, right? 3 components of the velocity for both objects. But how many equations I have? I have only 4 equations. So it will actually depend on the details of my collision. Okay, so let's write this down in 2D and 3D. The details of the collision are important to find the final velocities. Good. Now, let me also work a little bit more on this total momentum conservation, that concept. Now, if I have, let's say, 2 masses, m1 and m2. Let's say they are moving with velocity v1 and v2. Here's the thing. What's the total momentum? Total momentum is, well, m1 v1 plus m2 v2. I'll do something which looks very strange at first, but let me write this in a slightly different way. I would like to write this as total mass times some velocity. Okay? So I will actually say, I'll take out m1 plus m2 out. So I'll have m1 v1 plus m2 v2 divided by m1 plus m2. So this is the total mass. And that quantity, I will call it VCM. Okay, which is the time derivative of the following quantity, m times x1 plus m2 times x2 divided by total mass. And that is going to be what I'll call XCM, the center of mass position. So basically what I'm telling you is that the total momentum of a system is its total mass times the velocity of the center of mass. Now, one way, obviously I haven't done something super interesting. I just multiplied and divided by total mass once you look at it. But this definition is going to be extremely important, because although I haven't done it, it's going to hold also as a vector quantity. Okay? Where, let me tell you that our center of mass will be just m1 times position of the first particle in the 3 dimensions and m2 times position of the second particle divided by m1 plus m2. And I will actually be able to generalize this to more than 2 masses. I will say center of mass of a more general system is going to be m1r1 plus m2 r2 plus, it goes all the way how many masses you have, 1 m2 plus dot dot dot. So I'll just basically maybe I should sum up if I have n masses, mi ri divided by sum over I equals 1 to n mi the total mass. So let me write this in words. Total momentum is total mass times velocity of center of mass. So when I say the momentum of a system is conserved, if the mass of that system is not changing, it tells me that the velocity of the center of mass of that system is conserved. And when does that apply? When is the velocity of center of mass conserved? Whenever my system is a closed system, if there are no external forces on the system. So here is something interesting. That's why center of mass is so important. Think of a gymnast, okay? Some very complicated center of some very complicated object. It has many small parts that are tied together by molecular forces. So what he can do is he can jump, and he can, I don't know how to do this, but he, rotates around himself a few times, and then lands on his feet somehow, amazingly. So his body goes through very complicated motions. However, if I just look at his center of mass, center of mass doesn't care about the interactions between parts of the system. It only cares about external forces. So if I look at his center of mass, although his motion is very complicated, this will just be a uniform parabola. Center of mass moves as if it's like a stone which has all the mass. It's like a point particle. Okay. So this will just go on a parabola. Okay. So that point is almost, and for certain purposes, we can regard all the mass of the object to be concentrated at the center of mass. For example, the total momentum, hey, it's as if there is a point particle at the center of mass moving with the velocity of center of mass. In general, what we will do is we'll talk about all motion. We'll split it into two. We'll say motion is motion of center of mass plus rotations around center of mass. So that's in general any complicated kind of motion we will be able to break up into the motion of center of mass and rotations of the objects around the center of mass. Now, for the next lecture, I'll actually look at this motion of center of mass. More specifically, I'll look at situations where center of mass doesn't move. And starting in 3 days, in our next lecture, we'll start talking about rotation motion around center of mass. Okay? So basically, this is a recipe for the rest of our course. We'll look at first motion of center of mass and then rotations around center of mass. I'll come back in 10 minutes.